So our last topic will be finite fields. So let's say we have a finite field F with characteristic P. The characteristic of a ring is the least number P that you can add 1 to itself to get 0. This characteristic for a finite field must be a prime number, and the size of the finite field is a power of that prime. So let's prove the theorem. So the characteristic of a field could be 0, and that's just the situation where 1, 1 plus 1, 1 plus 1 plus 1, and so on, never gets you 0. So no sum of 1s can ever equal the 0 in the ring. Well, if that's the case, this gives an infinite list of elements in your field F, which obviously cannot happen because I have a finite field. If any two of these list elements happen to be the same, then you could subtract the smaller from the larger and you get a sum of 1s equaling 0. So the characteristic of a finite field cannot be 0. Now let's say P is A times B with A and B less than P. So let's say I can write my characteristic P as the product of two smaller numbers. So let's say P is not prime. So if P is not prime, then we have 0 is P times 1. And just to be clear of what I mean by this notation is what I'm going to use to abbreviate 1 plus 1 plus 1 plus 1 P times. So this is the same as A times 1 times B times 1. And I'm in a field F, which is an integral domain. In an integral domain, when you have the product of two ring elements equaling 0, one of them has to be 0. So either A times 1 equals 0 or B times 1 equals 0. Lightning bolt, that's a contradiction because P is the smallest number that I can ever find to give me a sum of 1s equaling 0. But if A and B are less than P, then I found a smaller value of 1s that adds to 0. So that can't happen. Thus, I've verified the statement that P is prime. So P is a prime number, and to finish the proof, I will show that the size of your finite field is actually a power of a prime. Now to do that, I'm going to define a ring homomorphism. So I'm going to define a function phi that goes from the integers and lands in my finite field. And I'm going to define this by phi of n is n times 1, which is 1 plus 1 plus 1 plus a bunch of 1s n times. And if n happens to be negative, then I will add a bunch of negative 1s together. So it's not difficult to prove that this is a ring homomorphism. It's a routine verification, so I'm not going to check it right now, but it's not difficult to prove that it is indeed a ring homomorphism with kernel given by pz. The characteristic of the ring is p. So that means every time I add together a multiple of p1s, I get out 0. So the kernel of phi is any multiple of the prime p. So the first isomorphism theorem for rings tells me that Zp, that's isomorphic to Z mod Pz. Z mod Pz, that's the kernel of the ring homomorphism. So the first isomorphism theorem for rings tells me that this is isomorphic to the image of the integers under phi. Okay, so this means, therefore, phi z, the image of the integers under phi, is a subfield of f. Zp is a field, and so I have a copy of Zp within the field f, the finite field. So f contains this field and more, so the name for that is f is a field extension, a finite extension. It's a finite field, so a finite extension of this subfield. So the dimension of f as a vector space over this subfield is some number n. So f is a vector space because it's a finite extension over this subfield. So let's say its dimension is n, meaning that there's some basis, alpha 1 through alpha n, in f can be found such that I have a basis for f over phi of z. So I'm almost done, actually. That tells me the size of this finite field is the same as the size of every possible linear combination of my bases. So elements in my finite field look like linear combinations of these elements. So they look like a1 alpha 1 plus up to an alpha n, such that a1 up through an are elements in this subfield. This subfield is isomorphic to Zp. So I have p choices for this coefficient, p choices for a2, p choices for an. Each coefficient in front of my basis vectors can be one of p different values. So that means this is p to the n. Okay, well, there's a wonderful proof that a finite field has to have characteristic p and actually has to have a size of a prime power.